So good evening, everybody. It's a real pleasure to be here. And today, our session is going to be batteries for emerging economies. I'm standing here with really bright lights in my eyes. I can't actually see most of you. And we take light, we take energy for granted if we live in a rich world. But if you're in a poor world, you might not have a light at all. Roughly 675 million people worldwide don't have access to any electricity, and far more have very unreliable energy supplies. So my name's Charlotte Watts. I'm the chief scientist at the Foreign Commonwealth Development Office. So I'm a scientist seconded into government. And one of the pleasures and privileges of my role is to support and use the power of science and the opportunities of science and innovation to try and tackle major development challenges like that people don't have access to electricity. And clearly, batteries and storage are a really important part of the opportunity and the need that people in developing economies have. At the moment, if you're in a developing country, you'll have very commonly unreliable energy source, if any at all. People often rely on fossil fuel generators, be they diesel or batteries. And this adds up to a lot of emissions. The estimates think that these generators are the equivalent of between 700 to 1,000 large coal power stations. They also cost a lot of money. They're inexpensive, inefficient, and polluting. An estimated $28 to $50 billion a year alone is estimated are spent on running these polluting generators. So back in 2026, when the UK government hosted the COP, the big climate conference, the UK made a commitment to double our contributions to international climate finance. And as part of that, clean energy access was one of the core pillars that the UK committed to investing in and supporting. And within that, science, innovation, and technology was recognized as essential. So as part of that climate commitment, the UK government announced £1 billion worth of support for clean energy research, development, and demonstration programs with a core aim of accelerating the clean energy transition in developing countries. So we generated a fund. We called it the Ayrton Fund, named after a wonderful female engineer and an innovator, and also a suffragette who did some of the early research on electric arcs. When the teams were coming up with what should we call this initiative, I said, give me a good female scientist name. And Hertha Ayrton was the person who's inspiring in this area that we named this portfolio of investment after. And what this fund does is basically center around challenges. So we try and use research and innovation to solve problems and say, what's the types of combinations of science, economics, and so on that can move us forward. Essentially, this fund works around 12 different challenges. So it includes what are the next generation solar technologies that can be locally manufacturable? How do we think about sustainable cooling in an ever-warming world? It includes innovations in clean cooking, so people can move from, in many contexts, relying on firewood and charcoal, and also includes things like smart green grids, as well as the subject that you're going to hear about tonight on energy storage. So if you think about energy storage and a developing country we need it to be cheap, we need it to be effective, and we need it to be reliable so that it can provide a sustainable and reliable source of electricity to underserved households, to support the provision of services, and to enable businesses to create wealth and jobs so that countries can fuel their own way out of poverty. And that when these grids, or when this energy is unreliable, it is to detriment of economic growth. So the Ayrton Challenge on Energy Storage, which is led by the Faraday Institute, and that's convening the efforts of many partners and programs around the world, aims to support innovations that will reduce the cost and improve the performance of energy storage systems, as well as invest in e-mobility solutions, so things like electric motorbikes, or if you've been to Asia, electric tuk-tuks, for example, so you can think about what are cleaner ways of providing low-cost transport. The activities supported under this Challenge Fund include £5 million of R&D programs that the Faraday Institute delivers, and that includes cutting-edge research into battery technologies, such as these sodium-ion and flow batteries that you can hear a bit more about in a minute, but also supporting partnerships, international partners, including the UK, but many partners from across the developing world, both with academics and with companies who are deploying new and innovative energy storage technologies in different developing country contexts. This R&D sits within a wider ambition that we have. Clearly, even if you have the tech, the issue is how do you get it out so people can use it at scale, because that's ultimately what will make the difference. So there are also complementary components that work with partners to develop skills, to accelerate and support companies to go from a pilot to really providing major range of services, includes access to venture capital, and also how do you build new markets with some of these emerging economies. And a range of partners are involved in that, including the World Bank, the Global Battery Alliance, the Carbon Trust, the Shell Foundation, the Global Energy Alliance, and People for Planet as well. So many, many partners. So what you're going to hear about today is to give you a flavor of the types of partnerships that this initiative is supporting, and to bring that to life and to give you a bit more sense of the science and the opportunity underlying this initiative. I'm very privileged and delighted to have 3 research and innovation leaders who are playing an important role in facilitating this clean energy transition. So with that, I'm going to stop setting the scene and invite our first speaker to the portfolio. It's Emma Kendrick. Professor Emma Kendrick is a professor in energy materials, and she co-leads the energy materials group at the University of Birmingham. She's very eminent in her field. She's been involved in many projects funded through the Faraday Institution, Horizon Europe, and industry. And that includes the Faraday Institution project NextGenna, which is researching sodium-ion batteries. It's an area I'm really excited to hear about in a minute. And Emma's worked both in industry and academia in her career, and has recently been involved in a spin-out company from Birmingham University, Imperial, called About Energy. And what she's going to talk about today is sodium-ion batteries for emerging economies. So let's give her a round of applause.
Thank you very much for that really great introduction. So what I wanted to do today is introduce you to a little bit about materials for batteries and some of the thinking that we might need to do when we develop new battery technologies. One of my most, I suppose, pet subjects in a way is sodium-ion batteries. And so we can set the scene on the minerals and the materials that are used both for lithium, and then how that we can bring in sodium into these new emerging economies. And Charlotte has set a fantastic scene about why we need energy storage. And what I just wanted to show you here is the potential for solar. So in this diagram here, what you can see is the red is where you get the most energy, watt hours energy per kilowatt peak of energy production from solar globally. And what you can see here is where the red is. That's very much in these areas of emerging Economies. Now, we all have energy storage. We have it in our pockets. We have it on a mobile phone, laptop. We plug it in, we charge it, we take it away, we use it where we need to use it. But in these emerging technologies, we don't have a grid necessarily. So what we can do is then store that energy that's produced to be able to then power the mobile phone, electric cooking, or even the light that we need to do our homework at the end of the day. So what is the battery technology and how is it made? What we have here is an anode, a cathode. These are electrochemical or chemical storage for our energy. These are separated by an electrolyte. It doesn't conduct electrons, it only conducts ions, which means that when we use this, we have electrons that go around the external circuit. These electrons are collected by current collectors. We have aluminium on one side, the cathode, and we have copper on the other side for the anode. Then we have the active materials. These are the materials that actually store the energy. So we have graphite, typically for lithium-ion, on the anodic side or negative electrode. And then on the positive electrode, we have a transition metal oxide, or lithium transition metal oxide, made of nickel, manganese, cobalt, and lithium. These are all particulate, so lots of powder particles that are all stuck together with a glue or a polymer binder system. And then we add a conductive additive to make sure that we can actually transport the electrons with these particulate composite electrode designs, both in the anode and in the cathode. So now we have the electrolyte which separates it. This electrolyte has to be non-electronic conducting because otherwise we'd short-circuit our cell. So in order to maintain the distance or the separation between our anode and cathode, they don't touch, we actually have a polymer separator between the two as well. And this porous polymer separator allows our lithium to leave our anode or our graphite, enter our cathode, and then collect the electrons at the other side. And this then powers our storage device, or a device that we're trying to, in this case, a laptop. So there's lots of elements in batteries, and I've just highlighted the different elements that you can see here in a lithium-ion battery. Every single one that I've highlighted is a potential element in lithium-ion batteries. Also, every single one that I've highlighted is known as a critical material. So a critical material is a material that has a huge economic importance. And we all know batteries are actually really important technologies globally, both for energy storage, consumer electronics, but also storing electricity from renewables, also the automotive applications as well. So the other aspect of critical materials, apart from the economic importance, is the supply chain. So understanding where these materials come from, where they've traveled to, and where they end up. And the more complicated a supply chain, the more critical a material is. And I just want to give you an example of two materials here, lithium and cobalt, which are two of the key materials in these lithium-ion batteries. So lithium really comes from two places globally. South America, mainly Chile, and Australia. And in Chile, the lithium comes from what's called salars. And these are large open lakes of water in mountainous regions where you've got little pockets of high concentration of lithium in the water. What we do is then pump out that lithium. The lithium goes into large, this concentrate of lithium goes into large ponds. The water is evaporated, and then we reclaim the lithium chloride, which is then made into lithium carbonate and lithium hydroxide, which is used in the manufacture of compounds for these batteries. We also have Australia. Now, Australia, the rock actually, it comes from rock, and the rock is called spodumene. What you see here, though, is actually over 55% of the global lithium comes from Australia. However, it's not refined in Australia. All of it goes to China. It's then refined, and then it's spread out around the world for where it's needed and it has use. In Europe, however, we still get 68% of our lithium from the brines in Chile, and only 32% from hard rock from Australia through China. Cobalt, however, is a very different story. And I quite like this graphic because it shows you how complicated some of the supply chains are with these minerals. Now, over 70% of cobalt actually comes from one country, and that's the Democratic Republic of Congo in Africa. Now, if you have a look at the red line there, which is a cobalt ore, all of that is shipped out of Africa, and it goes to be refined in China, which is then shipped around the rest of the world. Now, cobalt is actually a byproduct of mining from nickel and copper. So you can see here some of the nickel and copper mines that are global as well. And you can see we actually have some small refineries in Europe for some nickel. So nickel is less of a critical material for us here in Europe, and it's actually named a strategic material rather than a critical material because it doesn't actually hit the criteria for both economic importance and supply chain risk. Whereas cobalt has an enormous supply chain risk because it's from one country through China where it's refined. So what can we do to improve this, or to improve the sustainability of these materials that we're now using for lithium-ion batteries? Well, we can use what's called this waste hierarchy, where we can reduce the elements that are used in the batteries, either by increasing the energy density, so we need less material. We can also increase the lifetime of the cell as well. If we increase the lifetime, we need less batteries coming through to replace the ones that reach to their end of life. We can then maybe reuse the batteries, and we can recycle the materials at end of life before going through disposal. If we talk about reduction, though, we can also substitute these critical materials for something else. And one of the things that we're looking at substituting is lithium for sodium. Still an alkali metal, very similar properties, and we're looking at substituting something like iron for cobalt. So we know that lithium mainly comes from two areas globally. Salt, or sodium, is much more geographically diverse. We can extract it from seawater. So anywhere that you've got a coast, we can extract sodium from. It's also mined. We can mine it as soda ash or rock salt, which you may already know that you've put on your chips at some point. And then we can refine this to produce the sodium carbonates and the lithium carbonates that we use in the batteries. Not only is it more abundant, 23.6 thousand ppm, compared to 20 ppm of lithium, it's also much cheaper. So we end up with a much cheaper solution at $710 per metric ton for sodium carbonate compared to $14,000 per metric ton, both for battery-grade materials. However, it does have a downside or an impact upon the electrochemistry and the design of our cells. Because sodium is heavier than lithium, that means the specific capacity is lower. Because sodium is also bigger, we end up with a lower volumetric energy density. And we also have a lower average voltage. So you can see here a lower electronegativity on the sodium, which means we end up with a lower energy density overall. But actually, does that really matter? If we don't need to carry batteries around in our pockets for our mobile phones, we're putting it in with solar to store the energy storage, then maybe energy density isn't quite as important as it is for some of the other technologies that we are developing. Iron also is far more abundant than cobalt, as you can see from here, 300 ppm compared to 25. Also meaning that the cost of it is significantly lower at $106 per metric ton compared to 51.5 thousand. So there's opportunities here with these materials to develop some new interesting technologies which compete or can directly compete with some of the lithium-ion technologies. If we look at the minerals that are mined and produced in Africa, they're actually really diverse. We have an awful lot of minerals that are currently mined. Some of them are shipped elsewhere. I've just heard this morning or this afternoon that a new lithium mine has actually opened in Nigeria as well. So there's a wealth of minerals here. What we really wouldn't like is for all of these minerals that happen, like the cobalt that's mined here, shipped over to China to then refine to ship back to the rest of the world. If we can actually mine, process, refine, and manufacture, we can reduce that supply chain considerably and start to manufacture new, interesting technologies for different types of energy storage devices. So we have some lithium here. We also have some sodium mined in Africa. And actually, if you see the fuzzy green around the outside of Africa, we can also get sodium from the sea, from the whole of the outside from there as well. The other interesting thing is iron. 2.9% of global production of iron ore actually comes from South Africa. One of the mines in Madagascar actually produces an ore called lepidolite. And if you're interested, we have some examples of this mica, which is one of the lithium ores that you can see outside. So how do we then manufacture a sodium cell? How is it different from a lithium cell? Well, actually, there's not a lot of difference. We still have the anode, the cathode, the electrolyte. We now just swap out the lithium for the sodium as a salt inside the electrolyte. We actually can also swap out the copper. We don't need copper anymore on this current collector because aluminium doesn't alloy with sodium like it does with lithium. We still have active material components. The graphite is now a hard carbon, and we can actually substitute the lithium and the cobalt in the layered oxide system for sodium and iron. This operates in a very similar way. We can shuttle the sodium ions in and out of this layered structure, and it expands and contracts as we do so. If we take too much sodium out, the structure will collapse, so we've got to be careful on how we manage it. And in terms of the anode, we can use a hard carbon. So we intercalate the sodium in between the turbostatic layers of the hard carbon, and then we precipitate out a small amount of sodium in the nanopores within this hard carbon structure. But the operation is the same. We produce the sodium ions from the anode. They travel across to the cathode, where they enter the layered oxide system with the electrons going around the external circuit. So we've been doing a lot of work at Birmingham and trying to optimize these sodium battery systems. This is the sodium layered oxide system, nickel, manganese, iron. You can see we've got some beautiful particles that have been manufactured there where we've carefully controlled the primary and the secondary particle sizes to try and optimize both the energy density and the lifetime of these systems. You can also see from this graph, so those that haven't seen a voltage profile before, as we charge, we remove the sodium from the layered oxide system until we reach a maximum voltage, hopefully not getting to the point of crystal structure collapse. And as we discharge, the sodium goes back into the system again. And we have a very small first cycle loss here. For the hard carbon, it's similar. We can sodiate the hard carbon, which goes down in this voltage profile here. This is the turbostatic layers that it inserts, and at the bottom we get this small precipitation of sodium in the nanopores, which is reversible. But we get quite a lot of first cycle loss here. And that first cycle loss is due to the sodium getting stuck in that hard carbon material and also the formation of an interface on the surface. So these are what are called half cells. They're tested against sodium metal, so it's not a full cell system. What we need to do now is actually put that anode and the cathode together to develop that full cell. Now, this is a full cell. It's a 3-electrode test, which means that we can monitor the full cell voltage profile and also the cathode and the anode independently at the same time. And you can see here that we've got, again, the first cycle loss that you would expect from your hard carbon. And what we need to do is make sure that we've got the right balance of our anode to cathode, because you can think about it, if you've got too little anode, you've got nowhere for the sodium to go. It will just plate out on your surface, and it will cause dendrites, which means you'll short-circuit your cell. If you have too much, you end up with a huge first cycle loss, which means you've got only a small amount of sodium that you can move between your anode and cathode, and your capacity and your energy density is reduced. And just by careful optimization of that mass balance or the capacity balance, you can actually improve the cycle life of the cell quite significantly. And here we've gone up to a voltage of 4.1. Interestingly, some of the near-commercial cells that are coming through are only cycling up to 4 volts because there's still some instability in these systems that need to be optimized. So some final thoughts. We've looked at reducing the amount of critical materials by substitution. But what happens when these materials come to end of life? Now, currently, for lithium-ion batteries, we can recycle them. We can put them through a shredder, as you can see here. We can collect the materials, separate them into their constituents to potentially reuse again, or maybe use them as a secondary ore rather than a primary ore. But at the moment, our lithium-ion battery cathodes are still quite expensive. They're high value. Lithium has got high value cobalt and nickel and also copper. So what happens if we now substitute for less valuable materials? Is it still economically viable to recycle? If it isn't, then what happens to the batteries and what do we do with them? And I'll leave you with that thought. I thank my group who've done most of this work and the funding bodies. Thank you for your attention.
Great, thank you. And that question at the end, I hope somebody's going to ask a bit more about that when we get to the Q&A a bit later on. So I'm now delighted to invite up our second speaker, David Howey. So Professor David Howey is Professor of Engineering Science at the University of Oxford, where he leads a research group focused on modelling, diagnostics and control of batteries. David leads the Faraday Institution Ayrton Challenge for Energy Storage project on battery performance and is a work package leader in the Faraday Institution's multi-scale modelling project. So David's going to come and talk about battery health and lifetime diagnostics. Thanks.
All right, well, thank you for the kind introduction. I'm sure I'm not the first person who said this, but it's a great honor to be here. Let me begin with a short story. Several years ago, when I was a doctoral student at Imperial College in London, I remember a very senior professor saying to me, "There's some excited young electrical engineering undergraduates over here. Could you just go and talk to them and calm them down a bit, please? Because they've developed a charity that's going to bring electricity access to people in Rwanda without a power grid." And, you know, I went and had a chat with these students. They were great. But I do remember thinking at the time, wow, they are being quite idealistic and maybe a little bit naive. Well, I'm pleased to say how wrong I was, because these three undergraduates, Mansour Hamayan, Laurent Van Hoek, and Chris Baker-Bryan, subsequently founded a company called Bbox, which is a spectacular energy company that's impacted the lives of about 4 million people. And it's a real privilege for me and my research group in Oxford now to collaborate with Bbox to try and understand and improve the operation of their systems, which are based, as we'll see in a minute, very much on battery technology. So what do they do? So Bbox provides off-grid solar energy systems for rural customers. Here's an example of one. This one's nice and light because we actually removed the batteries. They're being tested in my lab at the moment. I'll pop it down here. You can have a look later. What's inside one of those? Well, a bunch of lithium-ion cells, a bit like this. I'm sure some of you have seen these before. A bit like the cells you might have in a power tool, I guess, or an older style laptop. And some of Bbox's older technology uses lead-acid batteries, actually. So they've provided hundreds of thousands of these systems to people mainly in Sub-Saharan Africa, but also in parts of Asia and elsewhere. And I thought it'd be nice just to find out a little bit more from a very short video. So I'll play that now. It's actually from a competition entry that they recently applied for, but I think it tells the story really well. So let's have a listen.
Think when you live in darkness, always. I live with my mother, 4 sisters, and 3 brothers. Living in darkness is extremely difficult and dangerous.
When I was 15, I had something in the dark. Something bit my foot. The poison from the snake was so painful. I almost died that day.
Over 6 million people in Rwanda who don't have access to a grid connection today. Households living in darkness typically end their day at sunset. By having access to light, it allows them to improve their quality of life and spend more time together as a family and community. Rwanda's young population is extremely hungry for education. Providing them with a few extra hours of light every night will make a huge difference to their future.
By now with B-Box, I can study with my sisters. My grandmother can cook, and we can all feel safe.
After I brought the B-Box, I can study much more, and they help me have a job and support my family.
Sheikh Zayed's vision for sustainability is one that B-Box also aspires to. It's not just about providing clean energy to households in the developing world, but also building a network of support, of trained people in the local area, and make sure those solutions are maintained for many years to come.
You cannot think big in time you live in darkness.
So I think you can see there, some of the difference that these systems make in people's lives. Simple things that we take for granted. Light, which helps us with education. There's safety and enterprise and business. So one unique aspect of these products is that they all stream live information to the internet. And this provides a huge treasure trove of data for a battery geek, battery nerd like me. Sure, maybe I'm not the only one in the room. And we can use this kind of information to understand not only how batteries perform, but how people use energy in these situations as well. But it's not just for academic interest. We could actually use this information to engineer systems which provide uninterrupted access to vital electricity, giving all the benefits you just heard about in the video. So let me tell you how we've done that in 3 different ways through some of our work. So batteries form the heart of these off-grid solar systems, and also a big part of their construction cost, of course. The batteries in these systems, they need to be in tip-top condition, just like, our own hearts. And if there's a problem, a company like B-Box needs to know about it ahead of time so that they can make sure they order the right parts to get to the right places. These are often quite remote rural locations, and supply chains can take a while. They get a technician sent out, and they get the system repaired. But how do we make sure that a battery is actually healthy? Well, the first challenge is we need to know what condition it's in the first place. So let me tell you about a healthy battery. A healthy battery is characterized by 2 things. First, a capability to store lots of charge, and secondly, the ability to deliver that at the right rate. Now, Emma had some very nice pictures of how batteries operate, beautiful diagrams. My approach is slightly more engineering-y. So this is my model of a battery. Imagine a bucket filled with water with a pipe, and the bucket's on the top of a hill. The water in the bucket represents the charge, and the flow of water in the pipe represents current. I'm sure many of you will tell me later that this is a very bad model of a battery, but let's go with it for now. So what I want to tell you is that the size of the bucket in this case tells us the total amount of charge that we can store, and the size of the pipe basically dictates how quickly we can get that charge in and out. So that's the current that we can deliver. And as a battery ages and degrades over time, both the bucket gets smaller, or if you can think of it like the fuel tank in your electric car getting smaller, and the pipe kind of gets clogged up as well, a bit like limescale, but not limescale, obviously. Most of us are very intuitively familiar with these ideas. We plug our phones in every night. We know what it means to charge them up. We also know what it means when our 3 or 4-year-old laptop suddenly switches off, when it actually said it had 10% state of charge. So I think we intuitively know what this means. And just as smartwatches, like this one I've got here, measure vital statistics for humans, like our heart rate or blood oxygen level. This one doesn't do that very well, I have to say. But battery products also have unique hardware and software within them and around them. Here's a picture of one that form what's called a battery management system. And this is a system that monitors vital information and controls the charging and discharging processes and makes sure that the system, of course, is safe for end users. So typically would measure currents, voltage, and temperature, and then generate diagnostics like the state of charge that we all know about from our phone. So you could think of this like a smartwatch for batteries. And I was very pleased to find this picture because it has both a smartwatch and a battery management system in it. But did you know that actually measuring battery health is quite a difficult challenge? And to get an accurate health diagnostics, typically what we would do in the lab, in my lab or in Emma's lab, you'd take a battery and you'd do many hours, maybe many days of tests. You'd do controlled charge discharges, you might do some rapid load fluctuations and estimate the resistance and so on. And this takes quite specialized equipment and quite a lot of time. And it's very unreasonable to ask a customer to bring a system in every month or every 6 months to do these tests, to take it out of action for a day or whatever. It's a bit like asking, someone to go and have their pulse checked in a clinic out of town, take a day off work, when actually the smartwatch would do that just fine. So this smartwatch for batteries idea is what we've developed in my research group in Oxford in collaboration with Bbox over the last few years. It's a complicated picture, but basically what's happening on the left is we gather up measurements from their system, voltage, current, temperature. That goes through some algorithms which generate these kind of health diagnostics that I was talking about. And then we can extract things like how healthy is the battery, is it going to fail in the next few weeks or months, and so on. And this means the key thing here is we can do it without interruption. This is a difficult problem. One of the key challenges we had to solve was how to deal with noisy data and also interruptions in data. And so it's a bit like finding a needle in a haystack. We had to use some quite sort of cutting-edge machine learning techniques to basically find that needle and make sure that they run computationally efficiently. So let's have a look at some of the results. So if we zoom into this particular graph. Right, what have we got here? So think of this chart a little bit like a comparative leaderboard of lots of different batteries compared in their performance against each other. In fact, we've got 1,000 batteries here on this chart, okay? You could perhaps call this the energy storage Olympics, or maybe like the marathon. Anyway, so we've got 1,000 batteries here, and about half of them were specifically chosen because they were failing, and the other half are doing quite well. And roughly speaking, the red ones are doing badly, and the blue ones are doing quite well. And so you can see on this chart, typically in this particular data set, the ones that are doing badly, the resistance, this is what we're measuring, the internal resistance kind of goes along nice and smooth, and then suddenly heads upwards, and that's a bad sign. That's a bit like that pipe kind of clogging up that I showed you earlier. And what's behind this graph actually is that there was a substantial effort required to produce this. So it's sort of some color on the screen, but actually behind this is about 620 million rows of data from 1,000 Bbox products. And each of these spans up to about 2 years in life. All of these data sets had to be kind of carefully smoothed and calibrated for operational conditions as well, because the battery resistance is actually strongly impacted by things like temperature. So why do we care? So this information basically provides companies like Bbox with the kind of signal that they need to get the correct replacement battery out to people in time and to make sure that their electricity supply isn't interrupted. But we can do so much more than simple diagnostics. Armed with this huge amount of data, every product becomes a potential research lab. What do I mean by this? Well, battery testing, this is a battery tester. Battery testing is expensive. This shows about 8 different test channels. Each of these channels typically costs about £5,000 or more. So to understand the aging behavior of a battery, you would typically take 5, 10, 20 cells, connect them to some testers like this, and run tests that might span 6 to 12 months. Field data, such as the data I've showed you from BBox, can basically become a giant research lab. And it's not going to replace these kind of lab tests that we do here, but you could think of it as extending them in scale by orders of magnitude. As I mentioned earlier, BBox have hundreds of thousands of products in the field, so that's a huge lab. Battery aging is really complicated. Many of us within the Faraday Institution are working on understanding and modeling battery aging. It's caused by lots of different interacting mechanisms relating from mechanical effects like cracking and clogging to electrochemical mechanisms like growth of things that we don't want. In this case, lithium plating is one example here on this picture. But in the end, what we want to know is what impact does this have on a real system in specific application, and in this case, off-grid solar systems? So one example of what we've learned so far is that certain combinations of behavior are particularly detrimental for aging. In this case, the average temperature and the average state of charge are key indicators of more aging. There are other things on this graph, like how old is the battery, how many cycles it's done, and so on. Things that we know about, but here we can see directly for the specific batteries in the data set that the company has exactly what is going on. We can also see things about combinations of factors together. So one of the things that's not on this graph, but actually if you have temperature and high state of charge at the same time, that's also particularly detrimental, so something to avoid. These kinds of lifetime models are super important for companies who need to understand the value of their products, and also organizations concerned with insurance and warranties for battery products. I don't know how many of you drive an electric car. We've got an electric car. If you've got an electric car, well, imagine you have an electric car, and imagine that the battery warranty was 8 years, and your car is now 6 years old. This is actually my situation. Should I sell it? Not sure. How much is the remaining battery warranty worth is a key question. Should I sell the car before the warranty expires? Wouldn't it be great if I could buy an extended warranty? What's the value of that? To do this, an insurance company basically needs a lifetime model of the battery, much like if you buy medical insurance, there's some model of how much that's worth behind the scenes. So there's another thing we can do if every product becomes a lab. We can start making interventions to see if we can extend and improve the life of batteries. And this is super exciting. This is some current work that we're doing with the Faraday Institution. Just like a middle-aged guy like me going out running, maybe trying to eat more healthily and so on. Well, how does this work with a battery? Basically, one of the things we've realized is that in many of these systems, they're not actually used to their full capability every day. Or to put it another way, there's a buffer of charge to ensure that electricity is always delivered and people can do what they need without the system running out of power. So this gives some wiggle room to adjust things. It's not quite like going to the gym, but you could think of it in a similar kind of way. So one very simple adjustment we can make with battery operation is to adjust the maximum voltage that we charge to. So if we go back to my very terrible model compared to Emma's models of the bucket up the hill, you can imagine that one of the things we could do is have a buffer at the top so we don't fill up to the very, very top of the charge, because we know that that condition is going to accelerate aging. And what's interesting is this might seem like a really small thing, right? Quite obvious, but actually it could extend the life quite significantly, maybe 10, 20%. Because the reactions that cause aging are strongly related to voltage. So at the moment we've got this project where we're actually taking the kinds of cells that are used in these systems, which are not the same kinds of cells in terms of manufacturing quality as are used in, say, electric cars. And we're doing a whole raft of tests on these cells to try and understand how this kind of buffer can really help extend lifetime. And I'd say that this kind of understanding of control of battery life is equally as important as the kind of chemistry, materials chemistry things. Super exciting to have the talk before as well. the cool thing about this is that we could actually apply these ideas to many different battery technologies, from lithium-ion through lead-acid to sodium-ion and future tech like solid state as well. Batteries are a $55 billion industry, and 14 million electric vehicles were sold just last year. We're actually now in what I would call the sort of terawatt-hour domain of production. And I did a quick calculation on the train. A terawatt-hour of batteries, what is that? That's 100,000 million mobile phone batteries, okay? It's per year. So we're in sort of mind-boggling numbers now, and it'll get only greater as we go towards 2030. So as we move into these kind of larger and larger numbers of systems in our economies, it's really, really crucial that we understand how to intelligently use these systems and extend their life to get the maximum out of them, especially given the precious resources that we heard about earlier that go into making them in the first place. So the way that we use batteries can have a big impact on their performance. I've told you about 3 ideas from our lab, specifically focused on solar battery systems. First one was this idea of a smartwatch for batteries, monitoring health in real operation, in operando, not having to go in and do a specific test. I talked a little bit about the energy storage Olympics, kind of comparing the performance of lots of different systems and giving a fleet overview. And then finally, this idea of every product becoming a potential lab and sort of extending life and learning by doing and making interventions in the field to see what we can do to extend life. Quite soon, just to finish, we'll see many of these battery systems requiring a kind of passport, a battery passport. Sounds like a strange idea, a bit like the passport you might get for your pets when they go overseas. But ultimately, we actually need this kind of tool to track all of the information from manufacturing through to use, through to reuse, through to end of life and recycling in order to get the maximum benefits from these products and minimize the negative impacts. Through these kinds of efforts, we can make sure that all people in every part of the world have uninterrupted electricity. I'm very pleased that those students that I met at Imperial College were not calmed down, and indeed they pursued their vision and delivered an amazing company. And it's been great to work with them. So thank you very much for listening.
Fantastic, a really lovely complimentary presentation. So now my pleasure to introduce our third speaker, Okenwa Anayo Nas, who is founder and CEO of Nayo Tropical Technology. Anayo is founder and CEO of one of the top Nigerian solar firms, Nayo Tropical Technology Limited, which has now a team of 43 employees running 12 microgrids and providing clean solar power to 14,000 homes and businesses in Nigeria. Nayo holds a bachelor's degree in electrical and electronics engineering, and his company is at the forefront of renewable energy technology development in Africa for the past 2 decades. So we heard about the innovation of the students you had. I'm really delighted to invite Nayo to come and speak as an innovator who's really driving the clean energy transition in Nigeria. Over to you. Thank you.
Thank you.
A very good evening, ladies and gentlemen, and it's my pleasure and great privilege to be here to speak to you in this prestigious institution. I started my journey in the renewable energy space 30 years ago as an amateur radio enthusiast. And amateur radio in those days were guys who tried to hack radio signals, create small circuits, and exchange diagrams. It was rudimental, electronics. And the picture on the left-hand side, or my right-hand side, you could see me in 1997 with a group of friends and partners when we started IKE Solar in Nigeria. Actually, that was my first year in the university. Apologies that the picture is not so bright. Then there were no smartphones and high-resolution cameras. So it's just a small Canon camera. So it happened that this was my first year in the university in 1997. I attended a local exhibition, and I met the three gentlemen from Germany and Austria. They came to do an exhibition about solar panels, and they kept trying to explain to people about how this works, and nobody seems to understand it. So I kept watching what was going on, and I stepped in, and I joined in the explanation, and they were excited someone is coming to bail them out. And we struck this friendship, and it has lasted till today. So it is how my journey started in the energy access space till today. In 2004, when I graduated, a year after my graduation, I decided to go full business because I saw an opportunity in renewable energy, and I also saw value and impact, giving power for the first time to hundreds of homes, or if not thousands. But in my own small bit, try to make it a business so that it will be sustainable and self-driven. Within then, 2022, we've built well over 13 microgrids owned and operated by us, and well over 100 others across Africa, not just Nigeria, for other operators. We also build and develop our own small electronics like solar home systems and other renewable energy components. This creates a lot of opportunity for training, learning, and also for employment for young Nigerian youths. And again, the spin-off effects, people learning from you and moving on to develop similar things and bigger cannot be underestimated. The impact of what we do, you can imagine rural folks who produce agro foods on seasonal basis. They store this agro produce, there's their banks. They don't have access to banks, so this agro produce is their bank. And imagine selling it off as next to nothing because they have no good storage facility and they have no processing equipment apart from rudimental manual processing. Providing energy access gives them, for the first time, access to value-added processing right in their community. This in turn reduces the size of the finished produce and improves their income and their disposable income. So this in turn have a very diverse impact in their livelihoods. It gives them more money for education, gives them more money for healthcare, so they don't rely on support, on handouts from government or donors. So with access to energy, you can unlock better livelihoods for last-mile communities like where we operate. So this, for instance, gives them first-time opportunity to use productive use machines, electric machines for the first time. Like I just mentioned, that is the difference between selling at 30% less or 70% more. Because when you do that, the size of what you transport to the peri-urbans or to the city to sell is a bit reduced, so you pay less on transport, moving these processed goods to the urban area because you've processed. Now you're going to the market with premium products, so you're selling more for value. So this is an indirect way of seeing the impact of bringing energy to rural locations. Part of also what impact of our work in the rural parts of Nigeria and Africa is e-cooking. It's a quantum leap for a rural family to move from firewood and charcoal to e-cooking. They skip the transition from kerosene or gas to e-cooking because of access to energy. So this saves a whole lot of money. Also, impacts on their life. You can imagine the amount of health hazards cooking with firewood on daily basis to rural women and young girls in Africa. So our energy access provides easy transition from firewood to clean cooking. Also, part of what we do is that we provide green jobs. Green jobs have multiple facets to it. One is direct employment through working for us, and Others is like direct jobs to locals during the construction stage of our projects. Thirdly, we also provide spin-off opportunities. There's employment opportunities like people who help operate the sites, and also new businesses. For first time, you could create mobile money wallets for rural folks who have no access to physical banks because of availability of power. People can have access to through mobile apps for medical care without having a physical doctor right in front of them. So a whole lot of impact comes from operating in the rural areas. Thirdly, we also we provide access to new farming technologies and farming opportunities. Now, the amount of produce rural customers can produce within a square meter of land improved by sometimes 6 to 10 folds because of access to new farming processes and technology, which also could be supported by or is made possible by energy access or bringing power to these rural communities. Today, I also want to discuss our project with the Faraday Institute, funded by Shell Foundation and the FCDO. This project started sometime around the COVID 2020-2021, and we had a lot of glitch due to the COVID supply chain disruptions and lockdown and all that. But it finally took off. Basically, what we did was to select some popular battery chemistries in the market, that are mainstream batteries, which includes lead carbon. Lead carbon is a typical lead acid battery, with a lace of carbon to improve, to create some catalytic effect to improve the performance of the battery. Then the typical lead acid battery. Thirdly, the lithium iron phosphate, which is mainstream at the moment. We also tried our hands around getting NMC. NMC lithium is a tweak of the standard lithium iron phosphate, but we had challenges in integrating that because, again, we are doing this with commercially available systems. It becomes a challenge to get some of these manufacturers to communicate openly with you and cooperate on issues of integration, because we had to do a lot of hands-on development. I could recall during those days, we had to buy off-the-shelf components to create, hardware systems that could pick very, very, deep information from the batteries, which includes the cell resistance, cell voltages, and also current moving on each string of the batteries. So this was enough to make typical lead-acid batteries give us deep insight into what's going on inside typical lead batteries, like you could do on a typical lithium iron phosphate battery management systems. So it took us some time to get all these systems together. We had a partner, Fentech from Germany, who did more of the integration, while we put boots on ground to do the go into the field to test this, set up these systems and do the testing. Yeah. So this is a picture of a typical setup. On my left-hand side is the mini-grid side. A container box contains the equipment and the batteries, the solar panels, and the remote monitoring system. And in the field, you have the solar panels. You can see inside this white cabinet is the inverter system, while the black cabinets on the right-hand side is the battery racks. So this is just a snapshot of what we did for the purpose of time. I just wanted to use this just to show you, give you an insight to what we were able to achieve in the first 9 months. We were able to, the process is very simple. We run what we call a kind of column test, a full charge to 100%, then we'll discharge down to 0, and we measure what happened differently from when we did this at a specific interval. So we now set up intervals of 90 days. So every 90 days, we run this test, and we allow the systems to run in real live operation, powering the rural community. the after 90s. The aim of this is to, to better advise, would-be mini-grid developers or, people who want to apply this technology elsewhere on if what the manufacturers claim that these batteries do or what's inside it is exactly what, in fact, that's what the academia or the scientists need to do to checkmate, the commercial, people on what they put out there, any information they put out to the public. And again, energy saved is money saved. In technology or in energy storage or energy access, we try to keep the cost as low as possible, especially in Africa when we're doing remote last mile operations. Because if you increase the cost, you transfer costs to very low income demographics. So this is a typical test report from a lithium ion phosphate battery. In a nutshell, we got about, we noticed about 1.8% degradation, within the first 9 months. That's about 2.4 in a year. Theoretically, that is 24% in 10 years, but it doesn't really work that way. Everyone knows that. As it's not a linear, degradation. A whole lot of other conditions affect performance of battery that will accelerate the aging process, like temperature, which is key temperature. Then the round trip, load, that's the stress you put on the battery, also affects the rate of depletion of the plates or the materials. So I think Professor Emma has done justice to the internal chemistry of batteries. And Dave, you've spoken a lot around integration. So most of what we do is more like the real life application using these technologies to improve lives in rural Africa. I want to thank you. I made this very brief, so I won't bore you so much because, as I said, those before me have done justice to this. Thank you for having me, and it's a great honor and privilege speaking to you all today. Thank you.